my name is Tom Chiesa. Right, so I was also an alumni from Stony Brook University, so I was a part of the SPIR program, Chiesa. It was so many years ago. Right, I've had a couple of different careers. I started out in the defense industry for a while. I was also in automation controls. I started out with Lisa environmental automation. And then when I graduated, I ended up with Brookhaven Industries, a defense contracting company. And now I'm in Brookhaven National Laboratory, working on the NSLS II on National Synchrotron light source. So my background is pretty spread out. So I'm also technically an embedded systems designer. I work primarily with FPGAs, and I also work with high power systems. So basically, I guess I should take my hat off. I am bald, so this anyway. So I work with high power systems, and I also do controls of high power systems using FPGAs and processors, because technically there's also a processor on the side. But we'll get to that. So, as I said, who am I? I am an electrical engineer. They constantly push me in the software anyway, and that's fine. I think a lot of people have similar lives, lines like that. You know, where it's like, well, you know, you can do hardware, but can you do this and that and the other thing? Sure. So I have a master's degree from Stony Brook. I started out in chemical engineering here. I did about 3.5 years in chemical engineering. I minored in electrical engineering. And then I realized I liked that a lot more. I did an extra year to finish my electrical engineering degree. Then did the accelerated master's. So it was a very long time, a lot of engineering. What's nice about that is essentially I have a lot of heat transfer, fluid dynamics, programming, electricity. And it kind of works out pretty well for NSLS II because all of those things are involved. Like, for example, even just today, there's a superconducting magnet test going on. And I was able to talk to the mechanical engineer about the heat transfer elements in the cryogenic system. He was a little surprised. I knew all this stuff. So, you know, it's always nice to be broad. But there's no problem with being specific. So I didn't end up that way. So my specialties are FPGA digital firmware design and testing, power electronics hardware, and of course drinking coffee, because I can't get enough of that. Currently, I work at the National Synchrotron light source, I work at the National Lab, and I'm an electrical staff engineer specializing in magnet power supply control systems for accelerator applications. We'll talk about what that means. So my job is a little unique. You know, it's not like your standard, you know, I write code and go home kind of thing. I work for a very large machine, a world-class machine that essentially is called a Synchrotron light source. Those of you that don't know what that is, which probably most of you don't, it's basically a large microscope. It's a large machine that produces a very small amount of wattage at very high energies. So essentially what I'm going to lecture just like that. So the ring here is this is a very large ring, it's almost a mile. And what happens is if you have a beam of electrons that runs in the circle, in the storage ring, right? And what happens is that as the electron beam bends, it emits light to what we call beam lines. So all these beam lines are different. They're for different energies and for different scientific experiments. Some are doing structural biology, some are doing material science, some are doing soft X-rays, some are doing hard X-rays, some are doing infrared. So as far as the science goes, that's not really my job. I talk to a lot of scientists all the time, and they do cool stuff. But generally, my job is a couple of things. One is to keep the thing running. Okay, so there's a maintenance aspect. I guess One is a maintenance aspect, where I basically keep the machine running, make sure it's running smoothly. The other is I do development projects for the accelerator. So they'll want different magnet systems to do different things. They're constantly upgrading it. And I also do designs for other systems in the United States and elsewhere. So it's a very spread out job. But essentially what it does is, what I like about the light source is that you can do a lot of parallel science all at the same time. And part of it is like I feel like I'm giving back to the community, giving back to humanity, because all these people are super duper smart that are at these beam lines. They normally have 3 to 5 days of doing experiments, and they write papers based on that data. And it runs 24/7. So If the beam doesn't operate properly, most people look at to do their experiments. A lot of times we call them in the middle of the night. There's something called a beam dump where we basically lose electron beam, which means we lose light, which means everybody's experiments stop. So there's a lot of responsibility on the electrical engineering team in particular to keep things running. And there's a lot of other groups at NSLS II. So I sort of catered this presentation for just electrical engineering, but what I do, but there's so many groups for NSLS II. It's radio frequency, which is a very, very important group. There's the electrical engineering group, which basically handles power supply systems for the magnets and the controls. There's the beam position monitor group, which uses very high precision devices and detectors to look at where the beam is so that we can have closed loop feedback on the whole system. What's really amazing, many amazing things. If you ever take a tour of this place, I highly encourage it. It will blow your mind. You'll never know what anything is. I mean, I can work here for 40 years and I still won't know everything about the place. But essentially, it's a lot of feedback systems all working together and then maintaining stability for extremely long periods of time, which is pretty incredible. As far as a large engineering feat, it's phenomenal. I sort of joined after it was kind of up and running, and I replaced a bunch of retirees. But the guys that really built this place really know what they're doing. All right, so how does it really work? This is a very simple thing. There's a lot of physics that go on. One of the niceties of being in this department is I do get to go to something called accelerator school, where you have the opportunity as an engineer to learn the physics of the system, which is nice. A lot of it is over my head, frankly, but I get drips and drabs. Essentially what happens, how do we make up an electron beam? Just really quickly, we have a LINAC. So basically, you have a little emission of electrons that is accelerated through a linear accelerator. Then this circle, the small circle, is a booster that boosts up the energy to 3 gigaelectron volts for our system. And then it runs in the storage ring, which is this large outer ring. And here, what's really nice is they show you the dipole magnets. Essentially, we all know from basic physics that, if you have a magnetic field, the electron will follow in a circle. So what we're doing is we're basically trying to bend the electron beam so that the light comes out and we basically illuminate the beam. This entire system has magnets lining it. So there's solenoids in the LINAC, there's a bunch of correctors and dipole magnets in the booster, and the larger dipole magnets on the outer side. There's corrective magnets, there's all different types of magnets, all different sizes, and all of them meet different types of power supplies. The booster is probably the largest power supply. It is a ramping power supply, so it injects electrons into the beam every 2 minutes or so. The dipole power supply maintains all of the current in all of these magnets. These magnets bend the beam at 6 degrees, and there's 60 of them to make 360 degrees, and they require a very large amount of current. And basically just maintain the stability of the beam as well as bend it. So, and all around these arrays, and I'll show you another picture, there's girders and girders of magnets everywhere. Let's see, yeah, here we go. So this is a picture of our storage ring. So we're inside the tunnel now, which is normally in operations, you can't be here, there's radiation, right? But when we do maintenance and we do shutdowns and things, we have to go in here, we have to fix things, okay? So the magnets in the storage ring are lined up on girders. Here's the blue one's a dipole magnet. And then you have like sextipoles, correctors, all different types of magnets. The correctors do super fast corrections to the beams. So basically if like a truck drives by or something like that, there's some sort of disturbance it can correct for it. So we have fast orbit feedback systems, slow orbit feedback systems. Funny thing is, like, this ring is so big it's affected by the moon. Phases of the moon will actually affect the orbit of the electron beam. So we have to do slow corrections for that, fast corrections for other things. So it's a very big system. Everything is in vacuum, obviously. The electrons, it's an ultra high vacuum system, vacuum group that deals with that. So let me read what's here. So yeah, firmware software development using FPGAs, control software integration for the control power supplies that drive inductive magnet loads. So what's particular about our power supplies is everything's an inductive load. Magnet is an inductive load. Generally, power supplies don't typically like that, but we use closed current loop control. We manage to maintain very high precision. So we're talking on the level of like 10 ppm, 100 ppm systems here, such that, you have an electron beam, this magnetic field can't be moving a lot. It has to be very, very precise. So we spend a lot of time integrating diagnostics into our system to make sure that we actually get that result. Yeah, so I do maintenance and troubleshooting, as I said. They call me in the middle of the night when there's issues. And me, usually one technician, have to go in and fix things. It happens all the time. But we're generally pretty stable. I normally get called maybe 30 times a year, normally at 3 a.m. Or if there's a lightning storm. If there's a lightning storm, we're probably down. Because it's kind of funny, when there's a lightning bolt, okay, the booster ring is actually covered in dirt. And I think that's why it's so sensitive to ground potential. When there's a lightning bolt, normally there's a ground shift of some kind, and we either lose injection or we lose beam. So whenever there's a lightning storm in the summer, I'm always like really checking my phone. But anyway, so we do design and adaptation of system upgrades and accelerated development, like I said. So our group, our power supply group, we're kind of specialists. I would say I'm growing into that position. But there are specialists in my group that handle these things. And so we're collaborating with the electron ion collider, which many of you may have heard of at Brookhaven Lab. There's a new collider that's going to be developed. That's also world class. And I'm also currently working on the advanced light source upgrade. So there are several synchrotrons in the United States. The advanced light source in Berkeley. I'm probably going to be going to Berkeley next month to work on their booster. So we're providing power supply and control support for their system as well. So it's a very varied lifestyle. Some of it's maintenance, some of it's design, some of it's work for others. And that's what I do. Right. So magnet power supply diagnostics. Something I want to stress is what we do is not just power, and we don't just do power supplies. When something goes down or something is wrong or you're dealing with a very precise system, you need to have diagnostics built into your systems. So we have these up on, so basically when you walk up the ring, there's the first floor and then there's the second floor that we call the mezzanine, where it houses all these racks. These blue racks here, different groups have different racks. Beam position monitor group has their racks, power supply group has their racks. And so essentially we have power supplies that are for correctors, sextipoles, all types of magnets in here. We also have controls that go back to a control room, Ethernet buses and such, so that the control room can see everything that's going on. And so these racks are really, you can almost think of them as entire instruments. What they do is they monitor the magnetic fields as closely as possible. They control the power supplies to very, very high accuracy. We normally use 20-bit DACs for control. 20 bits is the highest I've ever dealt with. I mean, in other companies, 12 or 14 bits is completely fine. 20 is like, wow. Our ABCs are also 20 bits. I mean, we really try to get as precise as possible. The systems are relatively expensive, but it is a world-class machine. So the engineering parameters are kind of different. For example, our last presenter has to sell these things and they're getting commercial products. This is like, the product is the ring. And the precision, the world-class capabilities of our device is what we put our money into. So our design parameters are very different. We're very temperature stable. And so that allows us to work a certain angle on our engineering to allow for the best possible system and the most reliable system. So this is my last slide. So this is just a picture of like what you would see if you walk into NSLS II. There's a lot of these TV screens everywhere to tell you the status of the beam. If that blue line is up there, that's a good thing. All right, so normally we run, it's kind of funny, at least interesting to me, we run at 400 milliamps, sometimes 500 milliamps. The machine was designed for 500 milliamps. We're now stable running at 500 milliamps. But literally, like this is like the most essential form of current. It's literally electrons at vacuum. When we say 400 milliamps, it's not through a wire. It's literally just bunches of electrons. And this is measured very accurately. And basically, a lot of electrons are sprinkled in every 2 minutes that maintain the level of this magnet. Because you always have decay in the solder. Sometimes the booster will drop out, which means you can't inject anymore. And then you'll see this line start to decay. The decay is relatively exponential. The users, in this case, it's not a bad failure mode. The users will still get light, but that light will degrade to a certain level where they can't use it anymore. So there's basically maintaining this line to be flat and maintaining the beam lifetime is the most essential thing. And that's basically it. And like I said, we run at 500 milliamps. Also, there's different things that we do. One is, normally we're in operations, which means that we just provide the light to scientists that work on the beam lines. Additionally, we have these days between, we have to maintain the system, so we have built-in maintenance days. And then after that, there's normally studies. So there's a whole accelerator physics division that just works on studying the ring, improving the ring, developing it, making the beam better and better. And they do some interesting things that normally perturb the beam in such a way that they may have to call me in or something. And then we go back into operations. Right now, we're actually in a shutdown. So a few times a year, we shut down the ring for close to 2 to 3 weeks. And that's when a lot of the engineers and technicians have on the system, plumbing, upgrades and whatnot. And then we have to bring it all back up and make sure that it all works. It's pretty amazing. I mean, it's a very, very large system, and we keep just bringing it back up and making it work to the same high-class level. So it takes a large family to work this thing and make sure that it runs properly. And it really is a very different perspective. Like, when I was a design engineer in the defense industry, it was very like, this is my design, this is my board, this is my world, right? It's all me. I write the code, I build the circuit. And NSLS II, that's never the case. In NSLS II, you are part of a larger group. You're part of a very large group of very smart individuals, all having a specialty, all needing to do one particular thing, which is help humanity by producing this light. And so I feel like my heart is in the right place working for this place, and this is what I do. So that's it. Yeah. Any questions?
So I guess, like when some scientists, maybe they want to use infrared radiation and other ones they want to use for like hard soft rays, it's possible to do that at the same time, right?
Yes. So
how is that realized?
Well, that goes a little beyond my scope, if I'm being honest, but it's the way the ring is designed. So inside the storage ring, the way the dipole magnets are arranged, the way that monochromators are arranged, set, gives you different lights. So each beam line will produce a certain spectrum of light. And you would go, like, if you talk to a scientist, they go, oh, well, I work at QAS, or I work at, 7BM, or something like that. They all have different names. They're all designated for certain research. And the storage ring is tuned for that. So there's a bunch of things that happen in that circle. There's a bunch of insertion devices. So something I didn't really go into, which is essentially what you're hitting on here, is that there are insertion devices in the ring called undulators and wigglers. These can be active or passive. A lot of times they're just strips of permanent magnets. And what they do is they take the electron beam and then wiggle them at a certain period. Like quite literally, just floats up. They just wiggle. And that wiggle is associated with a certain spectrum of light. So not only do you get that bending, when you bend it, you produce the light, but you produce another bend with all these wiggles. And what you get is a certain period of light that is specific to what they want to work with. And the rest is filtered out to the monitor at each station. So that's essentially what we do. Undulators and wigglers are very similar. Some of them are permanent magnet systems, some of them are superconducting magnet systems. Normally these are produced by separate vendors. And then we have an insertion device group that works with these, tunes these. These are very smart physicists that know exactly what they want. And they design it for certain spectrums. All of these insertion devices typically have, especially if they're permanent magnet systems, they have a lot of mechatronics associated with them. Literally, they're like nanometer encoders. I once had to work on an insertion device. I don't normally like doing that because it's like literally a $3 million device. They're like, well, hey, there's something wrong. Can you fix it? I said, well, I have to touch it. Maybe break it even more if I want to fix it. But it was funny. They were having a problem with their encoder. They asked if I could look at it. And I started to look at it, and I said, this encoder is wiggling all over the place. And they're like, yeah, it's always going to move. It measures nanometers. It's like literally always just moving. So at Rockwell Automation, I used, their encoder systems, and they were micron. But the same Renishaw encoder was used for nanometer precision, which I thought was really crazy. So the whole thing, very heavy magnets, large arrays, and then they're motorized to change the gaps. You change this gap, you change the period, you change the frequency of light. That's essentially what answers your question. Anybody else? Any questions? All right. Thanks so much, man. Appreciate it.